Hello, everyone. This is Yiding Feng. I'm a fifth-year PhD student from Northwestern Computer Science. My research interests including online algorithm and mechanism design.
I would be happy to talk about my joint work with Red from Chicago, and the title of this paper is Batching and Optimal Multi-Stage Bipartite Allocations. First, let's discuss some of the motivation of this project. So we know that in lots of online markets, so there is a central question of requires a platform to dynamically matching the demand or service request to the supply or the service providers. And in all those applications, different platform allows different latency. For example, in the Google sponsor search, the Google needs to respond to every search request in a very short time period. However, in the food delivery service or the Amazon delivery service, the allowance for the latency is much higher. And in this application that allows some of the latency, platform can make the more efficient decision by using the batching. Specifically, it will grouping the demand request together by introducing some waiting time. And then it will make the stage-wise matching decision one for each of the batches. It's easy to say that this batching strategy will give more information about the future because it includes some of the future in the current decision. Therefore, if the total number of requests is fixed, more number of batches, or in other words, smaller size of each batches, means that the platform can make less informed decision. Therefore, in one extreme case where there is only a single batch, the problem the platform facing is basically need to find the in hindsight optimal matching. And in another extreme case where each batch only consider a single vertices, basically this means that the platform are facing the matching in a fully online fashion. And the natural question to be asked is how about the middle ground regime? And basically in this paper, we try to answer the following question. So let's fix a number of batches. How could we characterize the optimal efficiency performance of a matching or allocation algorithm? Before introducing the model considered in this paper, let's first revisit the classic model for online bipartite matching. So in an instance of online bipartite matching, we will give a bipartite graph, where one side of node will correspond to a supply node, which are given offline. And another side of node correspond to the demand request, which will arrive in an online fashion. And the matching algorithm need to make an irrevocable decision once a demand request arrives immediately. And there are some generalization of this online bipartite matching model. For example, vertex weight B matching, where each of the supply nodes on the offline side has a heterogeneous weight. And the number of online node matched to an offline node cannot be exceed the capacity, capital BJ. And we have other generalization like online budget allocation, where each of the supply nodes will associate with a budget, and every edge will associate with a BIJ. And there are some other variation, for example, stochastic matching, free disposal, stochastic reward, etc. And in this talk, we will mainly focus on the vertex weight B matching, and we will consider a special case where the capacity equals to 1. Additionally, we will assume that we will allow our matching algorithm to produce the fractional solution. Now we can present the model considered in this paper. Here, we are given capital K stage, and a new batch of demand nodes will arrive at each stage. And for example, we can have an instance where there will be 2 states, and therefore we will have 2 batches. And we can have another instance where there will be 4 stages, and therefore there will be 4 batches need to be matched. Now let's define the class of multi-stage matching algorithm. Basically, once a batch K arrives, this algorithm will observe its demand vertices as well as their indices edges. And then it will require us to make an irrevocable matching decision, which satisfies the following two constraints. First, for every demand vertices, we can match at most one unit of it. And for every supply vertices, in the current stage, the total unit we matched cannot exceed 1 minus yj, where yj is the current consumption of this supply vertices. In other words, the total unit has been matched in the previous stage. And our goal is to maximize the total weight of the matching, and we will consider competing with a benchmark which is the optimal in hindsight solution. In other words, optimal offline. Specifically, we will measure the performance of a matching algorithm using the notation of competitive ratio. And our goal is to identify the optimal competitive ratio of our model. And let me remind you that when capital K equals to 1, when there is only a single stage, this problem is a fully offline problem. And when number of stages equals to the number of demand vertices, and every batch size equals to 1, this corresponds to the fully online problem. And our formal research question is that in the middle ground regime of capital K batches, what will be the optimal competitive ratio? Now let's have a quick review what we know from the literature. First, we know that any ready allocation, in other words, in every stage always picks the max weight matching, will give us a half competitive. And if we're treating our batch arrival model as a fully online problem, in other words, we will proceed every demand vertices one by one. Then we know that the balance algorithm in the literature will give us 1 minus 1 competitive. And in the balance algorithm, it will work as follows. So for every online vertex I, it will be matched to a supply node J, which has the largest discounted weight, which is Wj times exponential penalty associated with its current consumption Yj. And there are some other related work, including the two-stage combinatorial optimization and other two-stage multi-stage matching for different models. Here is our main results. In this paper, we propose a time-efficient algorithm with competitive ratio equals to 1 minus 1 over k to the power of k, and we will denote this as gamma k. And we also show that there exists instances such as no matching algorithm would achieve a better competitive ratio against gamma k. And let me remind you that this gamma k is between 1 minus 1 over e and 1. And for two stages, the gamma 2 will equal to 3/4. And for three stages, it will equal to 90 over 27. And when capital K goes to infinite, the gamma k will converge to 1 minus 1 over e. And we can interpolate this as follows. So suppose the future batches are picking by the adversary. In the worst case, this benefit of batching will vanish exponentially fast in the number of batches. In other words, if we want to gain some efficiency improved benefit from the batching for a fairly large number of batches, then we need to require that the future batches, the future nodes will satisfy some pattern which cannot be picked by the adversary. And we also show that the same results hold for the vertex weight B matching, budget allocation, assortment, if we consider a fractional solution. And if we restrict to the integral solution, we show the same results hold for if we have the large budget assumption. In the remaining of this talk, we will introduce this optimal competitive multi-stage algorithm. And basically, there are two questions we need to answer. First, how to design this balanced allocation through a polynomial regularization. And second, how to analyze this algorithm and using a graph decomposition and LP primal dual analysis. Before we formally introduce our algorithm, let's first try to have some intuition of this model. Let's first consider a very simple example of two-stage, where in the first stage we have a complete graph. In this case, it seems that we should try to match every vertices on the offline side with equal probability, because all the offline nodes has an equal weight. And in this instance, this will induce a matching whose competitive ratio is 3/4. And how about we always match the online vertices to the offline vertices with the maximum weight? Well, in this simple example, if we're doing so, we will give a competitive ratio of 1/2. However, if we match them uniformly, and if the epsilon is sufficiently small, then the competitive ratio will convert to 3/4. But should we always try to match it fully balanced? Well, in this new example, we will see that if we match both supply nodes with uniform probability, the competitive ratio is 1/2. And if we match them proportion to their weight, then we should get a competitive ratio of 3/4. And therefore, those simple example suggesting that we need to have some hedging. Basically, we need to add more balance to our matching to be robust against any arriving graph in the future stage. And basically, the next question is how could we formalize this notion of balanced matching for the general graphs? And how should we impose it by our algorithm? And how could we analyze it? And here is our solution. So basically, we propose a strictly convex regularization, which pushes toward the balance allocation. And let me remind you that this kind of technique of regularization has been widely used in different areas. And now let me formally introduce what is this real regularization look like. Now suppose that we are at the K stage and we have the bipartite graph of UK, EK, and the current consumption of every supply node. Then we want to consider the following convex program, where the constraint is a matching constraint, and the objective function will contain two terms. The first term is corresponding to the total weight we get from the current stage matching. And the second term will be a regularizer terms. And here the function capital F will be some strictly convex function. And for example, we can imagine it as an exponential function, convex polynomial, negative entropy, etc. In order to have a better understanding of the convex program with the regularization, let's recall the balance algorithm in the online bipartite matching. Remember that it will continuously allocate the arriving vertex I to the supply node J, which has a maximum discounted weight. And it turns out that this balance algorithm can be solved as a special case of a regularized max weight matching if only one vertices arrive at a time. In other words, the batch size equals to 1. And also, the regularizer will be an exponential function. And if we think of the vector of the current consumption as the current offline allocation levels, then the gradient of the objective in the convex program will exactly equals to the discounted weight considered in the balance algorithm. In this sense, the balance algorithm can be solved as a continuous Frank Wolf or the conditional gradient ascent. Now let me remind you that in the balance algorithm, basically the same regularizer is used at every stage. For example, when there are two stages, then in order to attain the optimal competitive ratio, in the first stage, we should consider the quadratic regularization. And in the second stage, we should introduce no regularization. In other words, we should always try to find the maximum weight matching. And in a recent work, it has been shown that by doing this, we would attain the optimal competitive ratio. When we are moving from two-stage instance to general k-stage instance, then we should consider a polynomial of decreasing degrees. In those plots, the solid line corresponds to the small f. And let me remind you that the regularizer capital F will be the integral of the small f. And the dashed line will correspond to the exponential function, which are used in the balance algorithm. And let me put two remarks here. First, our small f will converge to its exponential function. And our sequence of small f is actually generated by a backward recursion equation. And indeed, this equation is actually a requirement in our primal dual proof of the competitive ratio analysis. And you can check our paper for more technical detail for this part. Now it's ready for us to describe our final algorithm. So we will first introduce those polynomials with decreasing degree use our backward recursion equation. And then in every stages, we will solve a fractional solution corresponding as a solution of the convex programming using the proper regularizer of the polynomial. And for example, in the last stage, the polynomial will have a degree 0, and therefore we are actually solving the max weight matching. So far, we have finished introducing our algorithm. And next, we will briefly introduce how should we use the primal dual framework to analyze the competitive ratio of our algorithm. And briefly speaking, our analysis follows the standard framework of the primal dual analysis, and it will work as follows. First, we can write down the linear program corresponding to the optimal offline, and then we can write its dual program. We can consider a primal assignment for the primal program corresponding to the x star solved in our algorithm. In other words, for every stage, we will solve a convex program. Next, our goal is to consider the following dual fitting task. So basically, we need to figure out a dual assignment which satisfies that our objective in the primal assignment should be equal to our objective for our dual assignment. And also, under this dual assignment, the dual constraint need to be approximately satisfied. Now the question is that how should we design such a dual construction which satisfies our dual fitting requirement? And to do this, we need to introduce a structural decomposition lemma. First, let me remind you that xk star is a fractional solution we solve from convex program at stage k. Now let's consider a subgraph which contains all the vertices in stage k. In other words, uk and v. And we will consider a subset of edges from ek. Basically, an edge ij in ek will be added here if their corresponding xk ij star is positive. And now we can consider the kinetic component of the induced subgraph. And we can argue that it will satisfy the following property. First, let's fix the arbitrary kinetic component and consider arbitrary 2 supply nodes within this kinetic component. Then we can define their discounted weight as the equation in the left-hand side. And we can argue that all those discounted weights of the supply node within the same kinetic component will be equal. And we will denote it as CKL. And the second property is that there doesn't exist edge in EK between UKL and VKL prime if CKL is smaller than CKL prime. And the last property, saturation, tells us all the vertices except the vertices in UK0, they will all be fully matched by our fractional solution xk star. And this structural decomposition lemma can be proved by the convex duality, in other words, KKT condition. And for the unweighted version, this is equivalent to the Edmonds scalar decomposition for bipartite graphs, which are also known as a matching skeleton. And this will give us all the property we need for dual construction. And specifically, we'll build our dual assignment stage by stage. Initially, we will initialize all the dual variables to be 0. And in every stage, we will find this structural decomposition and update the dual assignment corresponding to the CKL we defined on the previous page. And in a high level, this is a generalization of a primal dual framework, which has been used for online bipartite matching. And we generalize it to be the batch arrival with multiple fixed number of stages. And it can be shown that using this dual construction, the increment of the primal objective and dual objective in every stage will be equal to each other. And this is basically using the uniformity property and saturation property. And another lemma 2, which is the main technical lemma, is to argue that the dual construction will be approximately satisfied. And it will use the monotonicity property and uniformity property first. And then the final bound will be proved by the induction on K and using our recursion defined for our polynomials. And you are welcome to check more detail in our paper for this part. Now we have finished the high-level idea of our primal dual framework to analyze the competitive ratio of our algorithm. Next, we will just do a quick summary. In this paper, we consider multi-stage bipartite allocation with batch arrival. We consider both fractional solution and integral solution with large budget assumption. We identify a polynomial time algorithm with the optimal competitive ratio. Here is some open problem left from this paper. The main open problem is trying to identify the optimal competitive ratio for the integral k-stage matching. And for the special case of two-stage, it has been solved by our recent work. And we conjecture that the optimal competitive ratio remains unchanged if we are shifting from fractional setting to the integral setting. And as we mentioned in the earlier of this talk, the benefit of batching decrease exponentially fast when the number of batches goes to infinite. In other words, it would be reasonable to think about what about k-stage matching under some stochastic assumption. And third, is there some other model which captures this latency and efficiency trade-off?
This is the end of my talk. If you have any questions or comments for my talk or our paper, please feel free to connect me through my email. Thanks for your listening.